When people think of Germany, they usually picture luxury supercars flying down the road. But there's something Germans are even more proud of, a highway system where the idea of a speed limit almost doesn't exist. That system is the Autobahn. A network so advanced that even American engineers can't help but wonder, how does Germany operate one of the safest high-speed road systems on the planet? Behind what looks like an ordinary stretch of pavement is an entirely different philosophy of construction. A roadway must be built like an engineered structure, not just paved over soil. Curious how Germany uses special standards in cutting-edge construction technology to make the Autobahn the gold standard of modern transportation engineering? Let's uncover the secrets behind it with us now. Germany covers only 357,000 square kilometers, less than half the size of the U.S. state of Texas. Yet it has a highway density 7 times higher than the United States, with more than 8,000 miles of Autobahn stretching across the entire country. But unlike many countries that simply lay a layer of asphalt and call it a highway, Germany approaches road building with a completely different philosophy. A road must be built, not just paved. The structure of Germany's highways is built around 4 key layers: a compacted subgrade foundation, a stabilized subbase layer, a load-bearing base course, and a high-performance asphalt surface. This multi-layer structure prevents cracks, deformation, or rutting even when cars are traveling at 300 kilometers per hour. But materials are the real key. Germany developed advanced polymer-modified asphalts that can withstand summer temperatures up to 70 degrees Fahrenheit, yet remain flexible in winter to resist freeze-thaw cracking. These strict engineering standards are what make the Autobahn a highway network where high speed isn't just allowed, it's safely supported by world-class construction technology. And now let's begin with the very first step in building a German highway, when the entire route is still nothing more than forest. Before construction begins, the technical teams have to go through a long preparation phase: geological surveys, terrain analysis, environmental checks, and detailed construction planning. These steps determine where the road will run, how thick each structural layer needs to be, and which soil stabilization methods are suitable for each section. Only after all the data is fully reviewed and approved are crews allowed to begin actual on-site construction. When the construction site is officially handed over, the first job is to clear all trees, vegetation, topsoil, and natural obstacles to expose the original ground underneath. This step is essential because any remaining organic material can cause settlement or instability in the road foundation later on. Once the area is cleared, the crews begin cutting and filling the terrain. High hills are lowered, low areas are filled in, and the entire route is shaped to match the designed elevation, ensuring a continuous, smooth roadway without breaks or uneven levels. To make the ground level and stable, the next step is to use heavy vibratory rollers to compact the soil. Depending on the soil type and moisture level, the crews usually make 6 to 12 passes, with each vibration delivering an impact force of about 25 to 35 tons. The goal is to bring the soil up to the standard Proctor density, strong enough to carry the huge loads of European trucks. Next, heavy trucks bring in crushed stone and unload it section by section along the road. Right after that, a grading machine spreads the stone evenly, covering the entire surface to match the designed elevation. Next, a water truck sprays a thin layer of moisture to help the stones bond better during compaction. A bulldozer then reshapes the layer, making sure the thickness and flatness meet the required standards. Finally, a large vibratory roller compacts the material through multiple passes to create a strong upper base. This crushed stone layer acts as the load-bearing foundation, helping distribute vehicle pressure into the soil below and increasing the durability of the entire pavement structure. After the crushed soil and rock surface has been leveled and compacted, the concrete base layer is ready to be poured. Heavy concrete mixer trucks begin entering the site, carrying pre-mixed cement with the correct consistency. When they reach the designated section, the drum is lifted to unload the fresh concrete into the receiving area. At this stage, the ground is already covered with white protective sheets to prevent moisture loss and to keep the surface clean before the concrete is placed. The excavator uses its large bucket to scoop each batch of concrete and transfer it directly into the hopper of the slipform paver. Thanks to continuous loading, the paver receives a steady supply of concrete without interrupting the construction process. Next, the slipform paver receives the concrete from the hopper and uses an internal auger system to spread the material evenly across the full width of the road. Inside the machine, high-frequency vibrators compact the concrete, remove air bubbles, and ensure a uniform density. A shaping mold at the rear then presses and forms the concrete to the exact design dimensions, from thickness to cross-section. The entire process is guided by a laser-controlled system, guaranteeing precise smoothness and slope. With its continuous operation, the machine can build dozens of meters of roadway in just a few hours. The steel dowel bars are placed into the loading tray above the machine so they can be inserted into the fresh concrete. These bars increase durability, prevent cracking, and transfer loads between adjacent concrete slabs. The steel dowel bars are placed into the loading tray above the machine so they can be inserted into the fresh concrete. These bars increase durability, prevent cracking, and transfer loads between adjacent concrete slabs. The machine's mechanical system automatically pushes each dowel bar into the concrete at the correct depth, spacing, and position. This ensures the slabs remain stable under traffic and allows the roadway to behave as a continuous structure. Right after the concrete is shaped, long finishing arms sweep across the surface to smooth and lightly compress the top layer. These blades ensure the concrete surface is free of waves and achieves the required high-speed roadway finish. This step is crucial for maintaining long-term ride comfort and skid resistance. When completed, this concrete layer is usually about 40 centimeters thick. When the concrete surface begins to set, a specialized spraying truck applies a layer of curing compound to keep the concrete moist and prevent cracking during the hardening phase. This protective layer, usually paraffin-based or acrylic, forms a thin film that slows water evaporation inside the concrete, helping it reach its optimal strength. After about 30 to 60 minutes, when the concrete has set enough on the surface, specialized brushing machines are brought in to texture the pavement. Their high-speed rotating brushes lightly sweep the top layer, creating fine grooves that improve tire grip at high speeds. This step also removes any excess cement dust, leaving a clean and uniform surface before moving on to the joint cutting phase. Finally, a specialized cutter will create expansion joints at design intervals to control cracking and protect the pavement structure. Once completed, the concrete pavement will be left to cure for several days before the next step of asphalt paving. Now comes the most important step in building a highway: laying the asphalt. In modern European and German projects, asphalt paving technology has advanced far beyond what it used to be. Dump trucks bring in hot asphalt, kept at around 160 degrees Celsius, and unload it directly into the paver's hopper. From there, the conveyor system and augers continuously move the material toward the back, making sure the mix is spread evenly across the full width of the road. The real magic happens at the screed, the vibrating, tamping, and pressing unit at the rear, which can achieve 85 to 92% compaction while the asphalt is still extremely hot. This allows the layer to be shaped, compressed, and smoothed in a single pass. This method is especially effective for the surface coarse or stone mastic asphalt, which is only about 2 to 3 centimeters thick and cools very quickly. Using traditional vibratory rollers on such a thin layer can cause cracks or ripples, but with the automatic screed on modern pavers, the road surface stays perfectly smooth, well-textured, and uniform along the entire stretch. In the past, the process required multiple rollers, vibratory, static, and pneumatic, to achieve the proper density. Today, high-end asphalt pavers handle more than half of the compaction work inside the machine itself. The Vogella pavers from the Wergen Group are especially well regarded for their precision, material efficiency, and their ability to reduce roller work by 70 to 80% compared to older methods. After paving, a light steel roller may make one final pass to finish the surface, though many projects skip this entirely because the mat already meets standards straight out of the machine. Thanks to this new technology, asphalt paving is faster, more consistent, and ensures long-lasting highway quality for years of operation. Once the asphalt has cooled and reached full stability, the next step is applying the road markings that guide traffic. First, the crew uses laser measuring tools or guide strings to determine the exact position of each line, lane dividers, stop lines, and directional markings. After the layout is confirmed, the specialized striping machine is brought in. It usually applies thermoplastic reflective paint, which is heated to around 180 to 200 degrees Celsius to ensure maximum adhesion to the asphalt surface. As the machine moves, its spray head creates lines with the precise thickness and width required for highway standards, while glass beads are dropped onto the fresh paint. These tiny beads reflect car headlights at night, significantly improving visibility and safety. After just a few minutes of cooling, the markings harden, bond firmly to the pavement, and the roadway is ready for traffic, completing the surface of the new highway. The final step before completing the highway is installing the concrete barriers. These barriers are usually precast in a factory before being brought to the construction site. At the factory, each barrier is poured into high-precision steel molds to ensure all dimensions and angles are perfectly consistent. After pouring, vibrating tables compact the concrete, creating a smooth surface and increasing strength. Once the concrete reaches full hardness, each barrier is removed from the mold, quality checked, and numbered in the order they will be installed. At the site, cranes or specialized forklifts place the concrete segments exactly where the plans specify. Workers then secure them together using steel pins or bonding adhesive, forming a continuous and stable barrier line. This precast installation method speeds up construction, reduces road closure time, and improves safety during highway maintenance. After the concrete barriers are installed, the engineering team conducts a final inspection of the entire highway. They check road smoothness, drainage performance, surface traction, and the structural quality of every section. Each component is approved only when it fully meets all safety and technical standards, and only then is the highway allowed to open for use. After a highway has been in use for a while, typically after about 8 to 15 years of operation, the asphalt surface gradually wears down due to weather, heavy truck loads, and constant hot-cold cycles. And that's when the highway needs to be recycled to restore smoothness, grip, and structural life. The first step in this resurfacing process is milling off the old asphalt layer, usually between 2 and 10 centimeters deep depending on the level of damage. The machine grinds the old asphalt into small pieces, collects it onto a conveyor belt, and loads it directly into the truck behind. Milling removes only the worn-out top layer while keeping the underlying base and structure intact. This way, the road doesn't have to be rebuilt from scratch, which reduces cost and significantly shortens construction time. The milled asphalt, known as reclaimed asphalt pavement, is transported to a recycling plant. There, the material goes through a screening system to sort it by particle size and remove impurities such as soil, oversized stones, or metal pieces. The usable asphalt particles are then blended into uniform batches. This step is extremely important because RAP can have different levels of aging after years of service. Proper sorting and screening help control the quality and ensure that the recycled asphalt mix performs just as well as newly produced material. Once the RAP has been sorted, it's mixed together with new asphalt binder, fresh aggregates, and a rejuvenator. This additive helps restore the elasticity of the old binder that has oxidized over time. At the mixing plant, the RAP is gradually heated to avoid burning the aged asphalt, then combined with hot binder and aggregates according to a pre-calculated formula. Some modern asphalt plants can use 30–60% RAP, while still producing a mix that performs just as well as brand new asphalt. This step is crucial because it saves natural resources, reduces CO2 emissions, and lowers overall construction costs. Before the recycled asphalt layer is placed, the entire roadway surface must be thoroughly cleaned of dust, dirt, and debris to ensure maximum bonding. In this modern process, a single machine handles both tasks at once. As it moves forward, the front nozzles spray a thin layer of bonding material, the tack coat, directly onto the old pavement using asphalt emulsion or liquid asphalt. This layer acts like a glue that helps the recycled mix bond tightly to the existing surface and prevents any slipping or separation under heavy traffic. Right behind the spray bar, the same machine immediately places the recycled asphalt mix onto the tack-coated surface without any waiting time. The paver then spreads the hot mix to the design thickness, while the screed vibrates and compacts it continuously, forming a smooth and uniform layer with the proper initial density in a single pass. After the recycled asphalt is laid, both vibrating rollers and static rollers compact the mixture to ensure it reaches the required density, preventing future rutting or cracking. Once compaction is complete and the surface smoothness is checked, the roadway can be reopened, performing just like new. So you've just followed me through the entire process of building, maintaining, and recycling a modern highway in Germany. All the information in this video was gathered from multiple reliable sources. If you spot anything incorrect or have any questions, feel free to leave a comment below, and I'll see you in the next video.